LeetCode 35, search insert position in JavaScript. Given a sorted array of distinct integers, nums, and target, a number, return the index the target is found at, or the index where target would be inserted at, in order. Must write an algorithm O log n runtime complexity. Example 1. Nums is 1, 3, 5, 6. Target is 5. Target is found in nums at index 2, so we return 2. Example 2. Nums is 1, 3, 5, 6. Target is 2. Target's not in the array, but it would be inserted in order at index 1. So we return 1. Example 3. Nums is 1, 3, 5, 6. Target is 7. Target's not in the array. It would be appended to the array. So we'd have 1, 3, 5, 6, 7. It would go at insertion order 4. 0, 1, 2, 3, 4 at the end. The simple, obvious way to do that is a brute force solution of looping through the array and finding the element that is equal to or greater than, we can use the greater than or equal to operator, target, and then returning the index of that element. And finally, if we don't find an element that is greater than or equal to target, as in example 3, we return the length of the array, because it would be appended to that array. I'm going to do some diagramming for the next one. If we look at this algorithm here, constraints are that the array can be up to 10,000 long. So that's not a huge array of numbers. And each number can be up to, well, from negative 10,000 to positive 10,000 for each number. And they're distinct values sorted in ascending order. And so we have to find out where the target is. So if the array is, let's say, 10,000, we have 0 all the way down to 10,000, then we could divide this in half. Get the midpoint element, see if that's our target, and if it is, then we return that index. And if our target is greater than that element, then we can start looping from here. Or if our target is not greater than an element, then we'll start looping from here. So we have 3 conditions. Target is equal to the mid element. Okay, return target. Well, not return target. Return the index. Return the index. Target is greater than the mid element. Start loop. Start loop at 0. No, start loop at start equals the midpoint index. And then if otherwise, we're going to start is going to equal 0. So we're going to look at this first condition, look at the mid element, the index of that mid element. And what do we get the index from? So the index is 0 plus length divided by 2. So 5,000. In this example case of 10,000 elements from 0 to 10,000. If the element at index 5,000 is equal to our target, then we return the index at 5,000. We return that 5,000 would be the index there. We just return that 5,000. That's the index where we found the target at that index, so we're going to return that index. If our target is greater than that index, we're going to have a loop. So we're going to have a loop, and so where is our loop going to start? If it's greater than the midpoint, then we're going to start at our midpoint, plus 1, and we're going to loop through it. Otherwise, we're going to start at 0. And so in code, a slightly different version of that, not exactly that. There's our first one. There's the brute force approach. And let me go back and revisit that first brute force approach. The point of this is to get something that fucking works in the interview. So this shows the interviewer that you understood the question and you can make it work. Even though it's not optimized, it does the job. And the performance actually in this one is not so bad. But now moving on to the one we're talking about most recently, this improved linear binary search, partial binary search. We're just cutting it in half once. We're not keep cutting it in half as a typical binary search. So what we're going to do is we're going to get the mid element by taking the length of the array and using this bitwise operator to remove the decimal position and get assigned integral value. And then we're going to get the found for that midpoint element, and we're going to compare that found element to our start. And if it's equal to that, we can return it. We don't actually do that here. We have a little slightly different approach. So rather than having that base case of if the midpoint element is equal to found, then return that index, what we're going to do for our found index is we're going to just compare to see if our start is less than found. And if it is, then we're going to start at 0 for our loop. Okay, so we're starting at 0. Where are we ending at? Well, we're going to end at wherever we find it. So we're going to end at nums.length in the worst case, but that's only going to happen when we reach mid, because remember, target is less than found, so we're not even going to make it to mid in this case where start is 0. Because it's less than found, so we won't even make it till the end. Won't even make it to mid. It's less than mid. So we're going to check each one, and we're going to see, is that element greater than or equal to target? If it is, then return that index of that element, of the found element. And if we don't find anything, then again we return nums.length. Now in the case that target is greater than found, then we're going to start at the midpoint element. Start is going to be equal to that midpoint index. Sorry, the midpoint index. And so if start is going to be the midpoint index, and start is actually equal to that found element, then we're going to find it on the first iteration. So I just removed it and then decided I'd use that in the loop to just remove one line of code. So it's a little bit simpler, although it does require the loop be entered for one iteration if target happens to be our found element. You know, it's not really that big of a deal either way, so I just left it that way. Now we can move on up to the iterative binary search, where we continually cut this thing in half. And this is going to require a more sophisticated approach. We've got a bunch of variables down here. We've got end and start, and these things constantly get modified. Modifiable variables are declared with let. We're not going to keep we're not going to change things that have const, obviously, so use the strictest declaration possible. And const would be more strict than we could use, and this wouldn't work because we would have to modify these end and start. So that tells the reader that we're going to be modifying these variables, and we are. And start and end are going to be modified. I should put them in different order, shouldn't I? Start goes before end. Small detail, but probably a better way to do it. So while start is less than or equal to end, we're going to continue to get that midpoint element. So look back at this example here. We've got this midpoint element. So if start, in this situation, we get our midpoint element. And if the target is equal to the element, the found element at this midpoint element, then we're going to return that. Otherwise, if the target is greater than that, then we're going to have start is going to be equal to the mid index plus 1. Okay? That's if the target is greater than the midpoint. Otherwise, if the target is less than the midpoint element, end is going to be equal to mid minus 1. We're going to loop up until this one. Okay, so let's say we have our target is 7,500, for example, and we cut this in half, and it's greater than 5,000. 5,000. So okay, so it's greater. Our target is greater than 5,000. So now start is going to be equal to mid plus 1. End is still going to be 10,000. And we're going to have to chop that in half. So we have 5,000 plus 10,000 divided by 2 is going to be 7,500. Well, let's say, just for fun example, our target is 7,501. Okay. That's going to make it harder to find it on one iteration. Because if it were 7,500, we'd find it right away. 10,000 plus 5,000 is 15,000 divided by 2 is 7,500. And if the target we're looking for had the value of 7,500 and the element at index 7,500, just for example's sake, had the value 7,500, num 7,500 equals 7,500, and that's right here. If that can even be read, 7,500, not really. So we'll just say this one is 7,500. Get those two zeros. There we go. Then we would find it there. But let's say we're looking for, let's say target is equal to 7,501. So we cut this in half. We get 7,500. Then we have to ask our question again. First thing, is target equal to the found element? No, target is 7,501. Found element is 7,500. So now we have to look one greater than that. So start is going to be equal to, now start is going to be equal to mid plus 1. Mid was 7,500. So start's going to be 7,501. Okay, so now start's going to be 7,501. End is still going to be 10,000. So then we're going to cut that in half. So 7,501 7,500. No, 7,501. Start is 7,501. 7,501 for start. End is still 10,000. And that's 17,501 divided by 2. Floored would give us 8,750. That would be our new midpoint element. That again would be right here. So now it's going to be 8,750. Okay? 8,750. Now we have to ask, is our target greater than, is our target equal to 8,750? If the element of that index is also 8,750, for our hypothetical example. No, it's less than that. So now we have to set end to be 8749. So now end is going to be equal to mid minus 1. Mid index is 8750. End is going to be 8749. And you can see that we're going to quickly run out of examples. That's the reason I chose 7501, because this one's a rather messy one, because we have a lot of editing to do. We're going to have to keep going until we get all the way down to one example. And so let's just do that right now. Let's see if I can, can't get it just a new one. I have to trash this one. Just clear it. Let's say we had 3 things in here. Let's say our target, let's get a new example now. Let's say our target is 5. And we have 3 examples here. We have an array with one thing. We're all the way down to the last one. And to simplify that, we're going to create num's array that has only one element in it. And I'm going to ask you to have a little trust with me to say that this is going to be the same type of problem. That the problem the solution that I described before, where we're constantly either increasing the start or decreasing the end to be respectively mid plus 1 or mid minus 1, then this will be the same sort of problem. Well, target is 5, and let's say nums is going to either equal to 5, 4, or 6. Now in the case where nums is 5, start is 0, end is 0, mid is going to be 0, target is going to be equal to our found value. Target is going to be equal to that found index. And then we're going to return that index I. Well, in our code, we're going to call it mid. So now if target is 5 and mid is 4, let's say target is 5 and then target is going to be greater than our found value. Okay, so in that case, we have to have end minus 1. End is going to be equal to mid minus 1. Well, what was mid? Mid was 0. So now end is negative 1, and mid is 0. Start is 0, end is negative 1. That's our loop terminal condition. So our loop terminates when start and end cross. That's the key that we have to get to. That's when our loop terminates. Because it's going to come down to that in some cases. Now, in some cases, we're going to get lucky and we're eventually going to keep cutting it in half, and then we'll get the midpoint, maybe on the first one, maybe on the 7th one. But in many other cases, we're going to find that we get down to the very last element, and this is a case where we have to say is our very last element, or in this case, element 0, our very last element in this case, is it equal to found? If it is, then we return that index. Is it greater than found? Then we subtract 1. And in this case, if our index is 0, then end becomes negative 1. Start and end are overlapping. End is less than start. Start is here. End is now less than start. We terminate our loop and we return start. Start is index 0. So we're going to return the start index, which is 0. And that's, start is less than, not in this case. Obviously, we have to return 1. Start is less than end in this case. So end becomes negative 1. Start is less than end. Wait a second. Now I'm thinking here. The target is greater than found. Target is greater than found. We have to increase start, not decrease end. That's where I had a mistake. So we have to increase start. Right. Because target is greater than the found at the mid index. So we have to increase start. So now start is going to be equal to 1 and end is going to be equal to 0. So now start is 1 and we're going to return start. So we're going to return start, which is 1. Now let's say our found value is 6. Target is less than our found value. Now we have to decrease end. Target is less than found. So now we're going to return, now we're going to decrement end. End was 0. And we're going to return start, which is 0. So let's revisit that one more time. Why was start 1 in this case? Well, start was 1 because the found value 4, well, the target was greater than the found value. So we have to increment start. That's what we do in our loop. And then our loop terminates because start and end overlap and we return our start value. So now let's take a look at the code here for that. Here we have end is nums.length minus 1, start is 0. Okay, it's different than the other one. In the other one we had end to be nums.length because we're looping all the way until the end. This one we have to have nums.length minus 1. Start is 0. Because we're always going to have 1 in our array. If there's one element in the array's length is 1, start is 0, end is 0, as in our base case. I just showed you. So nums.length is 1, in this case. Minus 1 would be 0. Start is 0, and end is 0. Start is less than or equal to end. We're going to continue in this loop. Perform the tasks in here. Mid is equal to start plus end divided by 2 floored. 0. 0 plus 0 divided by 2 is 0. Floored is 0. Found is nums at mid. Nums at mid. Mid is 0. And so in this case it's 5. If found is equal to target, start is equal to mid. It's a little trick I did here. And it's just a bad habit I picked up from a company I worked at that said you can't use the return statement in the middle of a loop, put it after that. So it kind of stuck with me. It's a little idiosyncrasy of mine. I don't think it's wrong to put multiple return statements inside a function. I don't think it's wrong to put a return statement inside of a loop. But there are some companies, and this one is actually, it's Google. They have it in their coding guidelines. Just one of those little idiosyncrasies inside their coding guidelines that it kind of stuck with me for some odd reason. But start is equal to mid, and then we break, and then we return start at the end. That's in the case where target is found. Now, found is greater than our target. That's in this case here. Found is 6. Then start is going to be equal to mid plus 1. Start is going to be equal to, wait, the found element is greater than our target. That's this case, yeah. found element is great and is mid minus 1, right? Of course. Found element is greater than our target. Found element is greater than our target. That's 6. Then we're going to return mid minus 1. I've got these in different order in the code than I do in my pseudocode, and it's a little confusing for me. So this example here is matching to this, and the code below in that else block is matching to the preceding line in my pseudocode. So it's not a direct translation. So if the found is greater than our target, 6, then we're going to return mid minus 1, and is going to be mid minus 1. And then we're going to, let's see, go to the loop, and our loop terminates because now start is 0 and end is, let's see, mid minus 1, which is negative 1. Start is no longer less than or equal to end. Start is 0, end is negative 1. Terminate, return, start. Start is 0, return 0 in this case. Now in the other case where if found is not greater than target, so found is not target, not equal to target, it's not greater than target. So now we know that found is less than target. So here start is equal to mid plus 1. Mid was 0. 0 plus 1 is 1. Start becomes 1. In this example over here, we're saying that end is 0. Now start is 1. Start is no longer less than or equal to end. Start is 1, end is 0. Start is greater than end. It's not less than or equal to, it's greater than. So we break out of that and we return start. So we return 1 in this case because target is 5. 5 is greater than 4. 4 is at index 0, and we would have to put that 5 at index 1 to make that array in correct order. And so there you have it, folks. That's how to solve this problem using that O of log n performance. I mentioned before, we talked about a couple things before. We talked about simplicity of algorithm up in this very first one here, and then making things just slightly more sophisticated by cutting it in half once. And that actually had phenomenal performance, but we had pretty good performance in this last one, except the performance decreased on the smaller arrays. On this binary search algorithm, the performance was still good in small arrays, but for small arrays, I found that the better performance was actually the iterative brute force approach. And so now I can show a little more over-the-top sophisticated. It's a little grandiose, too much, but here you have it. It's a strategy design pattern. I think it's probably a little more code than you would actually need. Honestly, in my own code, I would probably use this one or maybe this one, and that this one is a little more complex than I like, and that this one is getting way too complex. It just makes it easier for humans to process simpler code. So I tend to make things easier for humans to process because human processing tends to be the source of bugs. And that's what we want to avoid the most. Right, we want to have good code that runs efficiently, and when it doesn't do what it's supposed to do, and when it hides bugs, that's bad. And so we're not going to have this perfect situation in real-world code. We may have data that doesn't match our expectations. Things become more complex. If you've ever worked as a software engineer, you know exactly what I'm talking about. Things get complicated. Simple is good. So, but that's the asterisk. That's what I'm saying. This is not the ideal way to do it, but here's a way that is actually an interesting way to illustrate the strategy design pattern. So now we can say, well, if the nums.length is less than 5,000, then we're going to do this modified binary search. Otherwise, we're going to do this full binary search. And then we're going to call, both of those functions have the same signature. And so this is actually the strategy design pattern. Based on the input, we're going to do either one of these, this function or this function, and we'll call it with the same parameters. And the search insert linear, which is the partial binary that I showed before, is right here. And this is the search insert binary. Both of these are hidden in scopes. They're essentially static, private, and since they're declared with const, final, they're unmodifiable, both inside the function, and of course they're inaccessible outside the function. And there you have it. This had the best performance of them all, and got phenomenal performance out of this in all ways. So this is basically kicking most of the other algorithms' ass, and there you have it. Your easy problem, once you scratch beneath the surface, a little more complex than it might have seemed in the beginning. Hope you like it, folks. Thank you for watching.